Okay, all right. So here we go, part 2, tree traversals. So we went over, or you all went over, binary search trees in general, kind of the idea of how they're set up, the structure of them. This is about how to traverse a binary search tree, okay? Whether it's to print out everything that's in it or to search for something. Usually it's used for search. So there's 2 types of search for binary search trees. There's depth first search and there is breadth first search, which you might have gone over a little bit in the previous session. All right, but first, to understand breadth first search, BFS, and depth first search, DFS, you have to understand stacks and queues. So we've gone over that before. Anyone remember what a stack is?
Stack is when like the most recent thing gets put on top, like a stack of plates.
Exactly, yeah. So a stack is last in, first out, right? So exactly, you've got a stack of plates, you put, or let's say a trays, right, in a cafeteria room. You go and you put your tray on, someone else goes and puts their tray, they finish lunch, they put their tray on the thing, and then Anna walks up and wants to eat something, goes and takes a tray off the thing to go fill it up. Anna took whoever put on the last tray, that's the tray that Anna takes off, right? So it's last in, first out. All right, what's a queue?
First in, first out.
Exactly, first in, first out. So it's like a queue, like a line in a grocery store, right? Like your line at the post office or whatever. It's exactly first in, first out. First person in line is the first person that gets seen and goes out of line. All right, so just quick comparison of stacks and queues. Stacks are last in, first out. And stacks is what gets used for depth first search. Elements are added and removed from the same end. It can be the top or the bottom, but they're added and removed from the same end. And queues are first in, first out. That's used for breadth first search. We'll go into more detail of it. Where elements are added at one end and removed from the other. Okay, so that's just stacks and queues. So now we can talk about breadth first and depth first search. So BFS stands for breadth first search. DFS stands for depth first search. So a breadth first search searches a tree level by level. So you start at the root, then you go to the next level, right? Level 0. Then you go to the next level, level 1, you check all of its children. You go to level 2, check all of those children, right? So you're going level by level. And that is a good way to search, especially when the target is closer to the source. It ends up finding the shortest path to your element, because it says, okay, hey, I'm starting at the root and I'm seeing on each one of these paths how it's going path by path, level by level. So it finds the shortest path to whatever you're searching for, and it's better when the target's closer to the source. Depth first search is different. Depth first search goes down a full path, all the way down from top to bottom, and then it goes to the next path, and the next one is going all the way down the tree. So what you use for that is a stack, okay? Depth first search uses a stack, and because recursion uses a call stack, right? We're pushing things onto the call stack, we're popping them off. Recursion takes care of that. You usually use recursion for depth first search. And that's better when the target's further from the source. So you just get a lot luckier if your target's further from the source, right? Because you are searching all the way down. You're going all the way down. You hit the end of the tree way before breadth first search does. Any questions so far? And then we'll go into some more detail on the individuals.
You don't know where the target is there one that's typically better to just use generally?
I want to fact check myself, but I think depth first search is slightly faster. So I think that people tend to use depth first search. But it totally depends. It depends how your tree is structured. It depends what values you're looking for. You need to think about what works best. So if you don't know where it is and it's all super random, probably depth first search has you a little bit at an advantage, but it just totally depends on your data and your tree and how you're implementing everything. So I'm sorry, I know that's very vague, but does that make sense? Okay, any other questions? Okay, so let's go into some detail. So in depth first search, you're trying to go as deep as possible down one path before you back up and try a different one. Okay, so it's like walking through a corn maze. You explore one path, you hit a dead end, you go back, you try a different path. And you keep doing that in the corn maze till you get all the way through. So there's 3 main ways to implement depth first search, and it basically just is talking about the order in which you go through the tree. But I kind of want to show you what depth first search looks like first, so I'm borrowing this from a blog. And so here we go. Try to zoom in. Okay, so depth first search, if this is just a visualization, if you're traversing this tree, you're starting with the root, you go down all the way down this first path till you hit a dead end. And now you're backing up and trying the next path, right? So now you go down and now you look in this path. And now we're backing up, trying the next path. So here, and now we're backing up, trying that last path. So now we just hit all of these, right? But we went in this order. Here, here to here. Okay? Breadth first search looks different. Breadth first search, you're starting at the root, and now you look at all of its kid nodes. And now you look at all of their kid nodes. And now you look at all of those nodes. And now you've seen them all. And you went level by level. Whereas depth first search, you were going path by path. Okay, any questions on that? Okay, so, okay. So yeah, there's 3 main ways to implement depth first search. You've got pre-order, in-order, and post-order. And this is just the different orders in which you can do depth first search. The most common one is an in-order traversal because it's how you would think of a tree. It's left, middle, right. But there's no other real reason for that. So pre-order, wait, any questions? Sorry, before I go more in depth on these 3 ways, does everyone understand these are all different ways to implement depth first search? It's just you're doing your algorithm very slightly differently. But this is for depth first search, how to get down a path. Any questions?
By order, do we mean the values themselves? The values of the nodes?
No, that's a good question. Right. Okay, I see what you mean, the order of the values. No, the order of the nodes. So the order of the nodes that you're reading the nodes in. Which is tied to the values, right? But it's not like it's only reading out 5, 4, 3.
Okay.
Yeah. Any other questions? Okay. So here we go. 3 main ways to implement depth first search. Pre-order. This looks at the root of the tree, looks at the root, then goes down everything to the left, then goes down everything to the right. So this is these functions can look really simple because they're using recursion, right? So first it's just got our base case. If the root's equal to null, it passes in a root. If the root is equal to null, return. Right? Done. We're through the tree. And you can imagine as you get more and more into each subtree, your root eventually becomes the leaves, and then the leaves kids are null. Okay, so this will return for you. So if root's equal to null, return. I put down here console.log. Let's say that you were just printing out the tree in this order. It would be console.log, or you could just, have your results array or something. So console.log root value. And now call the traversal on root left and root right. So all you're doing is this whole function is just printing something out and then adding, this is the important part, recursion uses a stack, it's adding the left node onto the stack and then the right node onto the stack. And because recursion, it ends up calling, so it goes to the left, adds on this call to the function to the left, adds on this call of the function to the right, but each call just keeps going through, printing things out until it's equal to null. So this will print out everything on the left and then everything on the right, but it's putting it all into a call stack. So we'll see how this looks more in detail in a second. I know that's a little confusing, but this is the pre-order DFS, right? First, we've got our base case. If root's equal to null, return. We print out the root. Remember, this is printing out the root, then the left subtree, then the right subtree. So we're printing out the root, and then we're calling traverse the left subtree and traverse the right subtree. So now I want everyone to take a minute and try and think about how this could look. You can write it down, how this function would look if we're doing an in-order traversal, where we print out the left subtree, then we print out the root, then we print out the right subtree. All right, this was pre-order, which is printing out the root, then the left and the right. So let me give you like 20 seconds to look at this. Think of how this would look like for left, root, right, and then we'll talk about how this changes. And let me know if there's any questions. Okay, any ideas on how this would look if we're doing an in-order traversal, which prints out the left subtree, then the root, and then the right subtree?
You just change the order. You throw the console log between the root left and root right.
Exactly. Awesome. So we've got our base case, and then we print out we call this function to print out the left subtree, and then we log out the root value, and then we put out the right subtree. And I think I go into an example where we can kind of see how that looks. Oh, maybe it was I'll find you an example. Kind of showing how this looks a little bit more. All right, so now you saw, this is the most common one. We're using recursion, so if you did this iteratively, you would need to add in a stack yourself. Because it's recursion, it's adding in the stack for you, so it can do it a lot. So it makes it look a lot simpler. And it's calling things in the correct order, but here we're just traversing down the left subtree. And you can imagine, right? This whole thing won't return until the root's null. So this calls it and keeps console logging everything on the left side until that returns, pops up, console's this that was pushed on that right side, so it goes down the whole left subtree, and it's just popping on everything on the left subtree, left side first, and then the right side of each one of those roots, right? And it's console logging out the root node at each level of the subtree. So it's popping on everything to the left, shoots up, pops on everything to the right, prints out the middle, pops on everything to the right. All right, now post order is left, right, root. All right, so this one was left, root, right. What does left, right, root look like? What would post order look like? Any guesses?
Same as Jennifer told, just put console log after both the verbs function.
Yeah, put console log below both functions, exactly. So there, we're gonna have our base case, right? If root's equal to null, return. Post order on the left side, on the right side, and then log out the root. Okay, so just to give you an idea that like, okay, hey, recursion is using a stack for us, how would this look iteratively? you need to implement the stack. So this looks a little more complicated, but you can see you pass in a root. If there's no root, this would be, just return. If you're, sorry, I did a different one where one was console logging and one is pushing it onto a return array. So here, this would just return an empty result array. Otherwise, you have to create your own stack. So first you push the root onto the stack, and then you say, okay, great, current node is equal to root. And now while that current node exists, stack length is greater than 0. And I might have actually, anyway, well, I might need to fix something in this function. We're going to go through the leftmost node and push all those nodes onto the stack. So we're going to, okay, while current node exists, push current node on, current node gets current node to the left. So this just keeps going everything to the left and pushing it all onto the stack, right? And now it's going to, now that everything from the left is all pushed on, it's going to pop off that current node, the leftmost node, pops it off and puts it onto our result stack, onto a result array. And now current node, now that we've finished everything on the leftmost side, now current node's going to move to the right. And that's either null or, and it just popped off one of these things from the stack. And there's a bunch of things on the stack, right? So now current node moves to the right. Now it's either null or there is something that's still, so it's a leaf node, or there's something that's in the stack. If there is something that's, if it wasn't null, if it wasn't a leaf node, go and push on everything to that one's left. And you keep doing this. You basically just keep going through all the way to the left as much as you can. Then you say, okay, great, let me pop one up, go all the way, go to the right, go all the way to the left, etc. Does that make sense? A little bit? Let me see if I have it. Actually, yeah, okay. I have an explanation, so let me try to do that. So this is the same exact thing as our recursive. It's actually, it's an in-order traversal. It's the same thing as this in-order traversal for depth first search. It's just doing it iteratively. So the stack basically just helps us make sure we're doing everything in the correct order. So this is saying while a current node exists, the loop goes all the way to the left, pushing on the nodes as it goes. Then when current node is null, it pops that one from the stack. So it says, okay, I have visited this node. I've gone through all the way down to the bottom. Now go to the right child from the bottom, like the closest, most right child. So it just goes right down there. It doesn't go all the way back up to the right. It goes from the leftmost child, find the node that's closest to the bottom that splits off to the right. Does that make any sense? Any questions about that? That is depth first search. Okay, I'll try to find a good visualization of that in a second. Okay, so breadth first search is, remember, that one's going layer by layer. And because this one's going layer by layer, it's not going all the way down, this one's using a queue. And it says, okay, great, nodes are coming, I'm putting on a root, I'm putting on its kids, and then I want to process it in that order. I want to process the root, then its kids, and then their kids. So you also actually need, oh, did I show you? Did I show you this? Oh yeah, I did. Okay, so for breadth first search, I want to go into a little more detail here because I have a really good visualization. So breadth first search uses a queue, and we talked about that, right? Queue is first in, first out. So items get added to one side and they get removed from the other. So like this, and then remove from the other. Exactly. Okay. So breadth first search, we just need to be a little bit aware because we're not using recursion. We need to make sure that if we're pushing on a node and its kids, that we don't keep pushing on. We don't say, oh, hey, push on the sibling of this and push on the sibling of this, and we're putting on the same nodes or same kids every single time, and we get into an infinite loop. So you actually need two data structures for breadth first search. You need a queue, which is going to say, hey, here are the nodes that I want to, that I need to process. And we also need to actually have a hash map that's going to tell us, hey, I have visited these nodes. So basically, before we add a neighbor, right? So we want to make sure that, okay, there were 4, there's a parent, and it had 2 kids, and then they had, each one of those has 2 kids, and so now we've got 4 neighbors, right? And we're trying to add each neighbor onto the queue. We want to make sure that when we process it, we're popping it off the queue, and we're making sure that, hey, we say this one was already, we've processed it, we've visited it. So to do that, we just add it to a visited hash. Okay. I know this is what we're doing here. Okay. All right, but the main data structure it's using is a queue. So here's what this looks like. And this one you do iteratively, right? We're not trying to use a stack. So this one you do with iteration. For breadth first search, we're obviously saying, hey, if there's no root, you got nothing. Otherwise, push the root onto the queue and say, while there's something on the queue, we are going to take the current node off of the queue. So first that's the root, and we're gonna put that value onto our result array. And then we say, okay, if there's the current node, so at first it's our root, if our root has a left child, push on that child. If it has a right child, push on that child. And now loop back through again, right? Pop off that child, push it on to the result array. If it exists to the left, push it on to, push that child's left node onto the queue, right? So we're just basically visiting each one of these, and we're making sure that the order that is put on the queue is the order it's coming off. We're not saying, hey, push this on, push on its kid, push on that kid, and go down the tree like that. We're saying, hey, push on this node, push on all of its children, and now read out its children, push on those children. But as we're popping things off from the queue, it's keeping that order of the siblings and then the children. And it just loops through in that way, in that format. Okay. Any questions?
I have a question.
Yeah, please.
Yeah. If in Q, so we already told that in this binary tree, we can have the same value multiple times. And you show how to put double time 5 and double time 4. Anyway, in the example of the code you told us, it says that the current is the queue value, but if in the queue we have 2, 5, how the code will read?
That's a good question. So tell me if I'm understanding this correctly. You're saying that if there are duplicates and we're looking at this node, but this node is 5, like the value is 5, how does it know to look at this node and not this node whose value is also 5? Is that right?
Yes, and how it will later understand where is the current?
Good question. Can anybody tell me the answer to that? You can think about linked lists. Any ideas? Why does it not matter if the value is the same? Why does that not mess up our algorithm for seeing which node we're looking at?
because we comes from the previous to this one. I don't know. Yeah, I feel something like previous and next, but I cannot figure out how it works.
Yeah, you're
Is
pretty
it because
close.
it has like a, is it because it has like a specific location? So it's just related to like another like space?
Exactly. So these are all pointers, right? So this is pointing to a node whose value is 5. And this one here is pointing to a node whose value is 5. But those pointers are pointing to a node which is living at a certain place in memory. This pointer is not, remember, like if we're talking about pass by value, pass by reference, remember that, a node with a value of 5 is not equal to a node with a value of 5 unless you're comparing the pointers and they point to the same place in memory. So this pointer that says, hey, this node dot value is equal to 5. This node dot value is equal to 5. But this node is not equal to this node because those two pointers are not pointing at the same thing. So our algorithm is looking at, it's pushing a node on, but this node lives in memory space XA7Z10. And this node lives in memory space Z1534. And it is not going to confuse that they're the same because of their value, because the nodes are different, even if they have the same value. So it's a good question. Does that make sense?
Yes, I forget that we are pushing node, but not value.
Exactly. Yeah. And that's really important that we are pushing on a pointer to a node. We're not just pushing on a value. What we're looking at binary search trees is nodes and pointers. Okay, what we might want to get out of it, we might be searching for a value. We might be pushing on, you're pushing on a node with a value. We might be searching for a value. We might be ourselves doing something where we care about the value, but the data structure cares about the node, not the value. Yeah. Any other questions? Okay, so let me see if I can find, I had a really good, no. This is not what I wanted. I had up a very good visual for you all, and I must have exited out of it, and I am very sorry. Search. I might find it and just post it in the doc. This? Oh no, that's not it. No, I'll find it. But okay, so basically, to recap, we have two methods for searching binary search trees. We just go all the way down one path, and we go path by path, usually as far to the left, and then then the middle node, and then as far to the right as we can go. Or we have breadth first search, where we're going level by level. And depth first search can be a little bit faster, but it's just helpful if you think that your target is going to be farther from the source. Breadth first search is really good if you're just trying to find the shortest path to, the algorithm might take longer, but you're going to find the shortest path to where you're going by going parent to kid, and if your target is closer to the source. And breadth first search, you're using a queue. Depth first search, you can do it kind of 3 ways of order. You can print all the way to the left, root, right. You can do left, right, root. You can do right, left, right, root. I think I just said all 3. And I think that is it that we went over. So for binary search trees, this is really important to be able to just get down. Okay, someone might say in an interview, okay, implement breadth first search on a binary search tree. Implement depth first search on a binary search tree. That just came up for someone in an interview last week talking about binary search trees. So I just, practice implementing this. You can print stuff out as it goes. You can kind of see where it's going in the search tree. I'll send it out on Slack and I'll post in the document for our class a good visualization kind of showing depth first search a little better and the order in which it's going. But that's it. Any questions? All right. Okay, I'm going to stop recording.